All right, so for example 7 and 8, we're going to find a k value. All right, here's k. It's a constant multiplier. Let's find k such that the line, I guess this line, is tangent to the graph of this function. So this line has to be tangent to this function. In revisiting tangency, if a line is tangent to a function, then they share the same slopes and they share the same y-coordinates. So if that line's tangent to that function, we have to have the same y-coordinate because they meet at the same point, same y values, and they also have to have the same slope. We're trying to figure out what constant multiplier on this function would allow this graph, this line, to be tangent to this parabola. All right, so if we need the same y values, then what we're going to do is we're going to equate the functions. We're going to set the functions equal to each other. Equate functions. If they have to have the same slope at the point of tangency, then we want to set the slopes or the derivatives equal to each other. So equate derivatives. And then once we get two equations, we're going to solve the system. All right, so these two functions have to have the same y values and they have to have the same derivatives. So let me find the derivatives of each, since these are the y values. So let me find this derivative. So f prime of x is equal to, and if that's just a constant multiplier, we just apply the power rule. So you can just multiply the 2 into the k. So we'd have 2k, keep the x, reduce the exponent to 1. Let's go over here and find the derivative. Well, the derivative is just going to be the slope. So y prime equals -2, because that's the slope of this linear function. All right, so let's set the equations equal to each other. So let's do that first. I'll put a note what we're doing. We're going to equate functions. All right, so let's set kx squared equal to -2x plus 3. All right, well, we didn't get a lot from that, so let's move on to the derivatives. Let's set the derivatives equal. Equate derivatives. All right, so we're going to set 2kx equal to, well, that might help, -2. I'm going to divide both sides by 2. Cleans it up a little bit. Kx, oops. So kx is equal to -1. All right, so we equated the functions, we equated the derivatives. Now we have two equations. So we have this equation and we have this equation. So we want to somehow solve for k. All right, there's probably a few ways that we could proceed. Let me get this equation for the functions over here. So kx squared equals -2x plus 3. Okay, and in looking at the other equation right here, kx equals -1. If I could sub in -1 for the product kx, that might help me solve this equation. That's one way to solve this. Another way is to set each equation equal to k and then set those equations equal to each other. So I don't know if one way more than the other would be easier. So I think what I see is, since this is kx, I'm going to come up over here and I'm going to expand x squared. I'm actually going to make it x times x. Means I'm going to keep one of the x's to go with this k, and then I've got times the other x. It's kind of planning that I can then come over here to my second equation, kx, and where kx is, let's insert a -1. So I end up with -1 or -x equals -2x plus 3. Oh, that's not bad. Now let's add a 2x to the other side. It looks like I'm going to end up solving for x first, and then I can go back and find k. I'll cancel. What is this? This is 1x, so x equals 3. But that's not the answer to the question because we went back and read and it said find k. But that's okay. If I got x equals 3, then all I have to do is plug in 3 for x into one of the two equations. This one's more simple. So let me come up here and grab that equation. Kx equals -1. But if x is 3, this becomes 3k equals -1. Divide by 3. Divide by 3. So k is -1/3. As a visual for that, okay, let's go back to the original equations. So if I type in -2x plus 3 and type in now -1/3 x squared, which I've done, I've got it in y2 and y3. Let me come down here. That's dashed line. There we go. Let me graph this. All right, that's -2x plus 3. And did I not have that on? Oh, I do not have it on. The equal sign is unbolded, so that means it's stored in here, but it won't graph. So I arrow on top of the equal sign and press enter, and it turns the equation back on. Let me adjust my window. I'm going to do a zoom 6. All right, there's -2x plus 3 and -1/3 x squared. Yep, looks like this line is tangent to this graph at the x coordinate. I think we found 3. 1, 2, 3, yep. Okay, similar problem, but the algebra is going to be a little bit different in solving the system. So same idea. Let's set the equations equal to each other and the derivatives equal to each other. Well, we've got the two equations, the two y coordinates. Let's find the derivative. This derivative is going to be easy. This prime is going to be -3/4 because the derivative of a linear function is just the slope. This derivative, we need to bring up x out of the denominator, so keep k. This understood exponent is 1. When we bring it up, we adjust to a -1. So now the prime, let's use the constant multiple differentiation rule. So base of x, number exponent, multiply the exponent, get -k. Keep the base of x, subtract 1 is -2. Now for me, it might be helpful to rewrite this with a positive exponent. So writing it as a fraction, -k over x squared, that might be a better choice, okay, of using this version to solve. All right, so let's set the equations equal to each other. So k over x has to equal -3/4 x plus 3. Ooh. Well, I'll put that on hold for right now. Let me go to the derivatives. So the derivative would be -k over x squared equals this derivative, -3/4. Something I see that I might do right away is both these are negative, so I can actually multiply both sides by -1. Just get rid of those negatives. All right, so how to solve this? Well, I can solve it something like what I did up here. I can expand x squared and make it k over x times x and insert this equation for one of those factors. Well, that's a possibility. I could solve each of these equations for k and set those equations equal to each other. That's what I'm going to do. So let me solve this equation for k, which means I'm going to multiply both sides by x. So I'm going to multiply by x here to divide this x out and multiply this whole side of the equation by x. I'm going to come over here. So I end up with k equals -3/4 x squared and then plus 3x. All right, same thing down here. I'll multiply both sides by x squared. So times x squared over 1 times x squared over 1. So x squareds will divide out. So this equation will give us k equals 3/4 x squared. All right, now that I have two equations both equal to k, I'm going to set those equations equal to each other. So setting both of these equal. equals the other k. Yeah, I'm not going to work with fractions, so let's go ahead and multiply everything by 4. That will get rid of all the fractions. So multiplying everything by 4, that'll be negative 3x squared. That'll be 12x. And the 4's will divide out here, and I'll have 3x squared. I guess I'll add the 3x squared over. So let me add the 3x squared over, add 3x squared over. So 12x equals 6x squared. Now, if I'm going to solve this, I'm going to set it to 0. So I'd probably subtract the 12x over. So 0 equals 6x squared minus 12x. Come up here. Factor out a 6x. So that'd be x minus 2 equals 0. So just double check. Yeah, that looks good. So either 6x equals 0, divide by 6, divide by 6. So x equals 0, but that can't happen because when you go back up to the original equation, if 0 gets plugged in for x, you're dividing by 0. So this is what we call an extraneous solution, or x minus 2 equals 0. Add the 2. All right, we're not done though. We need to solve for k, but that's okay. I will go back into, looks like one of the two equations. I guess I'll go back to this equation right here. Let me pull down k equals 3/4 x squared. Let's insert a 2. That becomes 4, do the power first. That will divide out, so it looks like k is 3. All right, and one last problem, an application problem. You might want to pause the video and kind of read through all that language just to kind of familiarize yourself with position, velocity, and a little bit of acceleration. All right, average velocity is defined to be the change in distance divided by the change in time. The delta represents that word change. S is position. T is for time, so change in position over change in time. That's our average velocity. Our instantaneous velocity is at one particular moment in time, so you can think of this as like the secant line, because we have 2 points, and you can think of this as the slope of the tangent line, because we only have 1 point. We're looking for our velocity at a particular instant or moment, not over an interval of time. And this is very similar to our limit definition of a derivative. Well, it is. Notice that velocity, v of t, is equal to s prime of t. Either of those notations represent the same thing. So v for velocity, or s prime of t for velocity. And then the limit as time goes to 0 between 2 points we choose on the position function. So s is given to be the position function. V is for the velocity function. It's the derivative of the position function. Your velocity can be negative, 0, or positive. Speed, however, is always, it's never negative. It can be 0 or positive. And finally, into the problem, it gives us an equation of a position of a free-falling object under the influence of gravity, and it can be represented by this position equation. So the position s with respect to time at any given time is equal to negative 1/2 times gravity times the time squared plus V sub naught, or V sub 0, is your initial velocity times time. S subscript 0 is your distance off the ground, or above the ground, okay, or your initial height. So let's come over here and write those things down. All right, so V sub 0 is initial velocity. So we want to look for that language in the word problem so we know what number to put in for initial velocity. S sub 0 is your initial position. So somehow we need to extract where is this object starting from. Initial position. All right, and then also gravity, G. I've seen it two ways. If you're measuring it in meters per second, gravity is 9.8 meters per second squared. If you're measuring gravity in feet per second squared, then it's 32 feet per second squared. All right, ready to read the problem? It says a projectile is shot upward from the surface of the earth. Well, from that information, we know the initial position is 0 because we're on the surface of the earth, with an initial velocity of 120 meters per second. So I would say S sub 0 is 0. 120 is going to be your V sub 0. I see meters per second as my units, so I'm thinking, all right, we must be doing gravity in meters per second squared, so I'll use the number 9.8 when I need to for G in this equation. Use the position function for free-falling objects. What is its velocity in meters per second after 5 seconds and after 10 seconds? All right, so we want to find, what we're finding here is V of 5, or if you want to think of it as S prime of 5, those are equal. And then we're also finding V of 10, which is the derivative of S evaluated at 10. So let's go ahead and come up to the position equation and customize, put numbers in here, and then find its derivative using our shortcut differentiation rules. And then after we get the derivative, which is velocity, then we'll plug in each of these two values. All right, so the position function is -1/2. Gravity, we said we're going to use 9.8. We've still got t squared plus the initial velocity, 120 times t, plus S sub 0. Well, it's not like we're on a platform, so it's just plus 0. All right, let's find the prime. Actually, I'm going to clean this up a bit. That t squared, that exponent of 2 has nothing to do with these two factors, so I'm going to multiply these. I'm going to get -4.9, reattach the t squared. That might make it easier to find the derivative. So now let's find S prime of t, a derivative with respect to time. All right, so using the constant multiplier rule, let's multiply 2 times -4.9, so that's back to -9.8. Keep the base of t, drop to 1. The derivative of 120t is 120. All right, so V of 5, or S prime of 5, plug in 5, multiply it by -9.8, add 120. So V of 5, I actually got 71 meters per second. So 5 seconds after launch, the velocity is 71 meters per second. Let's see what happens 10 seconds after launch. Let's plug in 10. So I actually got 22 meters per second. So yeah, 5 seconds later, the velocity is not as high, so I guess it's probably getting to its peak and possibly thinking about turning around pretty soon. All right, so those were our basic differentiation rules and our rate of change example.